The area under the curve represents probability. The total area under the entire curve is always unity, that is 1. We may also express probability in percentage. So 1 is the same as 100%. If a random student were to be picked from this population, we will have the highest probability of picking a student weighing 150 pounds. We can also see that we have little or no chance of randomly picking a student who is less than 90 or more than 210 pounds. The curve is symmetrical about the mean, mu. Therefore, the area on the positive and negative sides of the mean is 0.5 each. Note that the normal distribution curve has two parallel units of measure along the x-axis. One unit of measure is the quantitative variable. In this case, it is the weight of students in pounds. It is expressed as an x value. The other unit is the z value. See the z formula from page 44 on your lecture notes. Z measures how many standard deviations an x value is away from the mean. The z value also helps us to determine the area under the curve. The area under the curve is the probability of occurrence. The table on page 6 helps us to find the probability of occurrence given a particular z value. Figure 4.3 in your lecture notes shows the area covered under the curve that is bounded by each pair of plus and minus z values. For minus to plus 1z, the area is 68.72%. For minus to plus 2z, the area is 95.45%, and for minus to plus 3z, the area is 99.73% of total area. This slide serves to highlight the importance of the Z formula in Chapter 4. You will need to apply this formula in all your calculations. Given a value of xi, which is a measurable unit, you can determine the number of standard deviations that xi is away from the mean. The required information you need are the population mean, mu, and the standard deviation, sigma. To be able to apply this formula, the sample size must be greater than 30. This is going to be a rather busy slide, but it will help us to understand how the standard deviation, sigma, is calculated. Column A shows the marks of 7 students ranging from 40 to 100. The average mark is 70. Column B shows the results of each individual student's mark minus the mean mark of 70. And column C shows the values after squaring the values in column B, that is, xi minus x bar squared. The total of all these numbers is 2,800. If we divide 2,800 by 7, we get the number 400 in column D. This number is also known as the variance. Square root the number of 400 and we get our final answer, which is sigma, and that is 20. Question: why divide by 7? Well, because the scores came from 7 students. So dividing by 7 will give us the per unit figure that can be used to compare with other standard deviations from other classes. Next question: why square root? Because we squared the numbers in column B in order to obtain the numbers under column C. So now the units of measure in column C is actually marks squared. The unit for standard deviation must be the same as the quantitative variable, that is marks. Therefore, we need to square root 400 marks squared to revert the units back to marks again. Some more questions. Why go through the trouble of squaring those numbers in column C? Because if we just total up the numbers in column B, the result is always 0. Why is that so? Because the positive and negative numbers cancel each other out exactly. So statisticians use a clever trick, and that is by squaring these numbers, the negative sign is removed. Note that A wider range of scores gives a greater sigma value than a narrower range of scores. You have come to the end of chapter 4.